your two organic cross-coupling reactions. Okay, remember that with Suzuki. The two things that you're going to be coupling are going to be some sort of an sp2 or a vinyl. Boronic acid or ester. And you're going to be coupling some sort of an sp2 or vinyl, organohalide, or a triplet. All right, so considering what those are, remember that when I say sp2, that means that it has to be on some sort of a carbon that is sp2 hybridized. Okay, so it'll be an sp2 hybridized carbon that's bound to some sort of a boronic acid like this, or ester. Cool. And then for your organohalide or triplet, we're going to have okay, so your triplet might be represented as OTF.
Sure, translate into which language?
Shut up. Okay. And then your good leaving groups. Okay, so the order that I'm drawing it in right now is the order of your leaving group capabilities. Okay, just as the leaving groups that you guys have learned from Orgo 1 in the past. Okay. All right, so yeah, once we have this, we can go ahead and discuss. I mean, it's slightly lagging behind. Oh, I think it's because of like the whole Siri activation that went slightly behind. Yeah, also if you guys could put your name in the chat, that would be great. Okay, so then some classic examples of Suzuki. Okay, so let's say I have something that looks like this. Okay, so then this is one of your examples of your boronic acids or esters. Okay, and then you can go ahead and then couple that with some sort of another type of double bond. Okay, so let's say I wanted to go ahead and I wanted to couple that with some sort of a vinyl bromide like this. Okay, the reagents that you would be using, again, don't worry too much about what the exact palladium reagents are. Just as long as you can identify that it's a palladium and some sort of base and heat, then you should be fine. So for example, you might have palladium, triphenylphosphine, triethylamine, and heat. Okay, before you go like, wait, Juan, that's slightly different from what you drew last week. Remember, it does not matter. Okay, so then when you go and then add these guys together, essentially remember that what you're adding in is your carbon chains, right? So right here you have a 4-carbon chain, and then over here you have a 6-carbon chain. Okay, so remember, do some very, very complicated math. If you add 4 carbons and 6 carbons together, you guess what? Get 10 carbons. Crazy how nature does that. Okay, so then once you go and then put those together, remember that you will have 6 carbons coming from 1. Okay, and then you'll have the other 4. Okay, so you go and then you create a new carbon-carbon bond like this, and then you will have the rest. Remember that in this case, the double bond is going to be trans, so you want to go and then keep it as such. And as I said that, I went and I drew a cis double bond. Cool. So remember, here are my 4 carbons, here are my 6 carbons. Together they unite and make 10 carbons. Cool. So that is a very typical example of Suzuki coupling. Remember, the nice thing about Suzuki coupling is that if you are feeling daring enough, you can go and then alter the stereochem. Okay, so if I wanted to go and then add in some sort of like a trans boronic acid or ester, like this, I can possibly go in and then add in something like, I don't know, like some sort of like an aromatic halide, so, or even a triplet. Okay, so note that I have this. I might have some excess of both of these, or some excess of like my starting material. I go and then I use my reagents. Then you can go and remember effectively add in both of these. Okay, so notice that in this case, you have 4 carbons here, and then you have 4 carbons over here as well. But do note this time that we have 2 different leaving groups. So because of that, we're going to need to go and then multiply the green reagent by 2 because we're going to be adding it twice. Okay, so once you do that, so you get your yellow reagent having added in. Okay, and then remember that your double bond has to be cis. Okay, and then those bonds in blue are the 2 new bonds that you're making. Cool, so if you have 8 carbons and 4 carbons, you should have a total of 12 carbons in your product. Okay, so it's just 4 carbons here, 4 carbons here, and then 4 carbons here, for a total of 12 carbons. Cool. And then that is just a very brief overview of some of the examples that you could do with Suzuki coupling. Does that make sense?
Yep. Thank
Cool.
you.
Now let's go and then talk about Heck. Okay, and you might be thinking
I
to
do
yourself,
have a question. Sorry. The triphenylphosphine, is that the ligand or what is it?
yeah, so it's a palladium, and so the triphenylphosphine would be coming together with the palladium to form some sort of like a coordinated coordinated palladium with triphenylphosphine ligands.
Okay, thank you.
I have a question.
Yes,
Why is the first product trans and the second product is cis?
because look at the double bonds in my starting material and my product, and my 2 starting materials. Here, notice that my starting material is trans, so I want to retain that stereochem here. Okay, here you see that my double bond is cis, so I want to go and then I want to keep that double bond cis over here. That makes sense?
Yes, thank you.
Cool. I always feel like whenever I'm about to make a joke, I always get cut off. So I don't know if that's just a sign that I shouldn't make the joke, but I'll make it anyway. Juan, why the heck do we keep doing this? Because it's good practice. It's a very useful reaction. Rosa, I see you being very into the joke. Okay. All right, so again, Heck is very similar to your Suzuki coupling, except the requirements are going to be slightly different. So similar to what we had earlier, we're going to have an sp2 or vinyl organohalide halide or triplet. I haven't really seen triplets as much with Heck, so I'm not sure if he has many backtest, so I'll just remove triplet for now. And then you're going to be coupling that with some sort of an sp2. Or vinyl, or I'd say rather an olefin or an alkene, or double bonds. With an sp2 or vinyl hydrogen. Okay, so what I mean by this is that something like this over here is fair game for a Heck reaction. And this one right here, let's do this. I'm not drawing a sad face because there are some exceptions, but in general, they would not really be good or good for a Heck reaction. So how do we know which case is which? I will get to that in a little bit. Okay, those would be a little bit more complicated Heck examples, which I don't think he might focus on too much in this class, but just for the purposes of showing you guys and expanding your brains, I will do it anyway. Okay, so let's go and take a look at that.
Sorry, Juan, could you scroll back up a bit for a second? Thank you.
Also, Juan, I had a question about the last or the second example in the Suzuki. Is there an extra, or are you missing a carbon in the final product?
Yeah, I was like looking at the chat and I was like, am I missing a carbon? Yes, I am. Yeah, thanks for catching that. So it should actually be, yeah, this is 5 carbons. I was not counting properly. So 5 plus 5 is in fact not 8 and is instead 10. So 10 plus 4 is 14. You have a total of 14 carbons. Well, before I move on, I just want to give a quick reminder. I have had some people asking me to if I'm sending out notes for certain days, or oh, I didn't get notes from certain day. Remember, I don't send out notes for every day. Usually I'll send out notes if I know that you guys have some big exam, or it was just a very loaded learning done session. But in general, always come into learning done expecting that I'm not going to send out the notes. Okay. If I do send out the notes, I'll send them out. But again, I'm not here to kind of just give you notes to write down. I do at least expect you guys to contribute a bit to the discussion. Okay, so let's go and take a look at this. So for your most classic, actually here I could talk a little bit about this example because it's not on pilot this week anymore. i.e. it was on pilot last week. So let's try these 2 Heck reactions here. Okay, so this and so trans versus cis. All right, so your intuition, if you're looking at this, might tell you, okay, if I have trans and cis and I just plop my phenyl right here or right here. No, you cannot just simply go and assume that. If you guys were paying attention to last week's pilot set, there was an entire meme on the first page dedicated to that. So pay attention to that in case you haven't seen it. So in order to do this, unfortunately, as much as it pains me to say, you have to go the long way and work through the mechanism. So to show you that, I will go and explain this. Okay, so first things first, what I want you guys to notice is your partial charges. So oxygen is partial negative. Wait, why is it partial negative? I forgot.
Sorry.
Go ahead.
Nah, you go.
Okay. Isn't it because the oxygen is more or less negative, so it'll tug on those electrons a bit more?
Yep, very good. So Oxygen is more electronegative, so you want to go and then do the little flippity flop in order to go and then flippity flop your charges. Sounds so cute. Wow. Yeah. So then, yeah. Now once you have flippity flopped all your charges, now you want to go and then insert your palladium into your phenyl bromide. Okay. So that would be the first step of your mechanism. Okay. Doesn't really help you in terms of like directionality, but the preparation of that or like that insertion is very, very important in case he does ask you to draw the mechanism. Okay, so then that would look like this. So take your little phenyl bromide. Okay, I'm going to be abbreviating the ligands as L just because, I don't know, L is shorter to write than PPH3. And if there's anywhere you want to have an L, it's in your palladium and not on your exam. Okay, yeah, so then the palladium goes and then inserts itself. I'll just put PDL2 over here with your bromide. And then for the next step of the mechanism, you want to go and kind of go and prepare that reactive intermediate. So to start off, it's very useful to go and then draw your starting material in the force perspective like this. Doing so allows you to go and then observe the stereochem easier, and it gets you ready for your syn periplanar elimination. Okay. So now here's where you want to go ahead and then add in your compound or your newly formed inserted palladium compound. Okay, remember that based off of these charges, partial negative, partial positive, partial negative, partial positive, right? Remember we want to go and then align that with just the opposite of what we have here. Okay, and then here we would say that this phenyl has a partial negative and the palladium has a partial positive. Okay, that's just pretty much the case with any metal with any organic compounds. So to go and then insert that, okay, all you would have to do is kind of go and then bring this phenyl group down here and then bring this guy up here, kicking off your bromide. Okay. That goes and then gives you your inserted product. Okay, now once you go ahead and do this, the next thing that you're going to want to do is to go and then, I always keep putting PD instead of pH. You want to go and then align this palladium with a proton that you're going to be ready to eliminate. Okay. So essentially to align that, you just want to go and then do a little rotation right here. Phenyl comes to the front, methyl comes to the back. Okay, and then once you have that, I know last week I showed you the mechanism where the hydrogen leaves as a hydride. I'll show you guys another version of the mechanism, one that you guys might be a little more familiar with based off of what you guys have learned, and that is treating this hydrogen as a proton rather than as a hydride. Okay, I've seen both versions of the mechanism, so they should be fine. But here, this would be a more clear use of your base. Okay, so you would go and then take that, eliminate right here, and then send this guy up. All right, and then doing so, ends up giving you a product that looks like this. Okay, or if you want to draw it a little more nicely, you certainly can. but do please keep in mind what just happened here. Okay, the stereochem that you observe is not the same as the stereochem that you had in the starting material, right? Particularly what I mean by that is that even though the methyl group was on the opposite side of the ester, the methyl group does not necessarily stay on the opposite side of the ester here, now being on the same side. Okay, so then that's why here in this case you would observe that product rather than the one that you might expect. Case in point being, drawing the mechanism is especially very, very important. Cool. Any questions on this?
What happens if you don't have like that group, like the ester group?
You don't need the ester group necessarily. I just use the ester group because it's a very classic example.
But what happens if you have a different group? How would you determine where the palladium adds to?
Oh, so like, yeah, in that case, you would have to like maybe like find a way to like deduce the charges, but if you can't find out where it adds to, then you would probably just end up with a mixture of products.
Okay. And also for Suzuki, we don't need to know the mechanism, right?
Nope, you don't.
Okay, thanks.
Yep, no problem. Cool. So just for the sake of not repeating the mechanism over again, just know that the same thing applies with the opposite mechanism, and I encourage you guys to try it out on your own. But know that when you do that, you'll end up getting the opposite stereoisomer. So you would have two different diastereomers of each other. Cool. Any questions on that before I show you guys a more unique example that I haven't necessarily shown in Learning Done before?
Wait, where does the diastereomer part come in? Like, is there a chiral center?
No, no chiral centers. You just have double bonds of different configurations. Okay, so here you see that you're going to have your, this is going to be your E, right? So, and then this is going to be Z. You don't necessarily need chiral centers. If you have a double bond, remember that double bonds don't have free rotation, so that's why they're considered diastereomers, because they're not mirror images of each other.
Okay, thank you.
Mm-hmm. All right. So now a bit of a, we're gonna go and then we're gonna add some seasoning to our Heck reactions. I'm gonna make it a little more spicy, so make sure you guys are ready to handle what you're about to see here. It always gets a lot more fun when you put food analogies into these types of things. Okay, so right off the bat, based off of what I told you about Heck before, what do you notice that might be problematic with this reaction?
There are no hydrogens on the double bond.
No hydrogens in the double bond. So previously I've told you don't do that for Heck. But what if I told you you actually did get something happening here? Let's see. So first things first, as we would want to do is, I'm going to skip the preparation of the ligand this time because you guys get the idea. But I would start off by going and drawing this in the fourth perspective. Let me actually put this one back. I'll put the phenyl over here. All right, so let's observe what our partial charges would be here. Okay, so remember that whenever you have an allyl group like this, whenever you have an R group, by hyperconjugation, that's ortho-para directing. Okay. First sign of literally your entire world's coming together with this class. It's like, what do you mean ortho-para directing? We didn't look at this for Suzuki and Heck. Well, guess what? Now it becomes important. Okay, so you have that. And then that means that if you were to go and then move your partial charges around, that means that this guy all the way up here would end up being partial positive. Okay, so what that corresponds to is this guy over here. So now let's go ahead and then insert our palladium. So then our phenyl group would come in over here. Okay, so then this comes and then attacks down here. This comes up here. Then your bromide will get kicked off. So then you end up with something that looks like this. Now, when you go in and try to find a proton to eliminate, notice that we don't have any protons over here, okay? We have all methyl groups here. So what does that mean for this reaction? Is the reaction gonna stop here?
No, it's going to take a hydrogen off one of the methyl groups.
Excellent, very good. So, or not from one of the methyl groups. The methyl groups are too far away for you to take a hydrogen off.
Propyl group.
Yeah, the propyl group, right. So you'll take it from this far away land right over here. Okay, so when you go and do this, so you would go and then this would come off, this would come off, and then what you would end up getting so here, let me define some stereochem here. Actually, not too necessary because all we have to figure is the regiochemistry. So when we do that, we're going to end up with, so your double bond would be here. On one side of the double bond, you're just going to have the rest of your, so now this becomes a propyl group, which used to be a butyl group. Okay, wait, yeah, it should have been a propyl group. I added an extra carbon here. Yeah, so then this now becomes an ethyl group. Okay. And then on the other side, you're going to have a phenyl group here. And then everything else on that side just stays like that, assuming I didn't add any. Did I add another carbon? Oh, I am adding extra carbons left and right today. Hello. So it would be like that. Okay. To draw it a little more nicely. So your product would either look like this. Erase this. Or like this. Cool. So very special rowdy case of your Heck reaction. So yeah, make sure that even if you can eliminate from one side, if you have another possibility for a proton on another side, then definitely go and then try that one out.
So to generate this like product on the right, you just rotate that like single bond, right? Like,
So your two different stereoisomers would depend on which proton you eliminated.
okay, got it. Thank you.
Mhm.